chloride is there, beryllium BeH2 is there, and whereas if you take the structural component here, lithium chloride, beryllium hydrate, barium chloride, okay, etc. Now what I am trying to say, if we carefully see lithium, beryllium and boron, okay, lithium, beryllium and boron, they have 1, 2, 3 valency electrons only, whereas some other such components are aluminium trichloride, AlCl3 and also BF3. So let us know limitations of the octet rule. Still so far we have seen what is an octet rule. In this class let me explain the octet rule. Though it is not universally accepted one, it is quite useful for understanding structures of the most of the organic compounds. What are the structures that are having organic compounds, especially carbon compounds, and it appears mainly to the second periodic elements of the periodic table. In case of exceptions, there are 3 major exceptions or limitations are there for this octet rule. The incomplete octet. What do you mean by incomplete octet? If you take a PCl5, phosphorus is a central atom. In some compounds, the number of electrons surrounding the central atom is less than 8. If it is less than 8. PCl5 I have taken as an example, but it is not best example for incomplete octet. Instead of that, we have some other elements having less than 4 valence electrons. Example, lithium chloride is there, okay, BeH2 is there, okay, and boron trichloride is there. These are best examples for this. So diagrammatically, lithium chloride, in between lithium and chloride you can see, and in between beryllium and hydrogen you can see here the structure how it is mentioned, and boron trichloride is there here. Now in fact lithium and Be, nothing but beryllium and boron have 1, 2, 3 valence electrons only. Some other such components are aluminium chloride, AlCl3 and BF3, and they are amazing examples. Ordered electrons which are not belongs to them, ordered electron molecules, in molecules with an added number. So what is an ordered number of electrons, like nitrous oxide, okay, nitrogen monoxide and nitrogen dioxide, okay. So here nitric oxide and NO2, nitrogen dioxide, NO, nitrous oxide. So the octet rule is not satisfied for the above said atoms. In fact, if you take NO, nitrous oxide, nothing but laughing gas, okay, octet rule is not satisfied. Why? Because nitrogen have specific electron set and oxygen have a specific electron set. And NO2 if you take here, it is also not satisfied octet rule here. Expanded octet, what is that? Elements in and beyond the third period of the periodic table, apart from 3s and 3p orbitals and 3d orbitals, also available for bonding. If you take in a number of compounds, these elements, there are more than 8 valency electrons around the central atom. In fact, this is termed as the expanded octet. The octet rule does not apply in such cases. Some of the examples of such compounds, let us take out them, which helps to understand this expanded octet. Expansion in the sense more than the normal electrons, valency electrons are more in number. SF6 is there, and H2SO4, nothing but sulfuric acid is also there. So these are all, and a number of coordination compounds are also taken as an example for expanded octet. Finally, here P of 3, okay, 10 electrons are there around the phosphorus atom. Now here sulfur is the central atom, you can see here, and how many electrons are there around it? 12 electrons are there. Now sulfur is in H2SO4 nothing but sulfuric acid. Sulfur is the central atom and 12 electrons are there around the sulfur atom. And if you take a sulfur dichloride, here the valence electrons and remaining electrons you can see clearly in the diagram. Okay. Now after that, interestingly, sulfur also forms many compounds in octet rule obeyed, which means sulfur generally forms many compounds. It is able to form different types of compounds, okay, in which octet rule is generally obeyed or applied to the sulfur compounds. Sulfur dichloride, sulfur atom has an octet electron, okay. Now apart from that, other drawbacks of the octet theory. What are the drawbacks of an octet theory? First one is, it is clear that octet rule is based upon the chemical inertness of noble gases. Inertness is nothing but introduction of zero group elements or noble gases. So it is clear that octet rule is applied only when there is an interference of noble gases. However, some noble gases, for example, xenon is a zero group or noble gas element, krypton is there, and also combined with oxygen and forms, and also fluorine also here involved to form a number of compounds. Here the compounds which are formed by xenon and krypton, when they combined with oxygen and the fluorine, it will be just like this: xenon difluoride, krypton difluoride, xenon XeOF2 are the different compounds which are formed when zero group or inert noble gases interact with oxygen and fluorine. Fluorides and etc. are going to be formed. This theory does not account for the shapes of molecules, and in fact it is clear that octet rule is based upon the chemical inertness of noble gases or zero group element. Here in case of it doesn't explains only it doesn't explain the relativity, or it doesn't explain the relative stability of the gases. It doesn't explain the stability of the molecules, being totally silent about the energy of a molecule. From the Cosils and Lewis treatment of formation of an ionic bond, as we have seen, Lewis explained how ionic bond is generally formed. It allows that formation of ionic compounds would primarily depend upon, first step, it is easy formation of the positive and negative ions from the respective neutral atoms. Positive and the negative ions are, so what do you mean by ionic formation? How ions are going to be formed? Ions are of two types, positive ions and negative ions are also. Here the arrangement of positive and negative ions in the solid, if you carefully see a solid, that is the lattice of crystalline compound. So arrangement of positive and negative ions in the solid. The formation of a positive ion involves ionization, formation of ionization or formation of ions, whereas removal of electrons from the neutral atom. When the electrons are going to be removed, and that of the negative ion formation generally seen here. Addition of electrons to the neutral atom. In case M and G is given here, chemistry affinity, it is the negative of energy change accompanying electron gain. Obviously, ionic bonds will be formed more easily between elements. Why? Because with comparatively low ionization enthalpy, and the elements with comparatively high value of negative electron gain enthalpy. Because of this, ionic bond formation is very much common. So most ionic compounds have cations derived from metallic elements, and whereas anions from non-metallic elements. So finally what I am telling you, if you take the ammonia, let us take ammonium. So ammonium here, ammonium ion NH4 plus made up of two metallic elements is an exception. Whereas in case it forms the cation, what is cation here? Cation of a number of ionic compounds. Ionic compounds in the crystalline state consisted of three-dimensional arrangement of cations and anions held together by Coulombic interaction energies. What is Coulombic interaction of energy? These compounds generally having a crystallize in different crystal structures determined by the size of the ions. Now their packing arrangement and other factors. The crystal structures of sodium chloride, if you take NaCl rock salt, for example, it is shown following a figure or diagram. If you take the structure of an NaCl, here you can see sodium, this is a sodium atom you can see here, chlorine, blue color dots that are nothing but sodium. In between them you can see the bond formation. Finally what I am telling you, rock salt structure M plus G plus electron gain, ionization is there, ionization enthalpy X into gram plus electron minus X minus G. Electron gain enthalpy, how to say that? As per the formula M plus G plus X minus G gives rise to Mx. So this one and this one both going to be combined. The electrons gain enthalpy delta EGH is the enthalpy change when a gas phase atom in its ground state gains an electron. What I am telling you, electron gain process may be exothermic or endothermic. Okay, electron gain is nothing but receiving. Electron receiving process, maybe it is an endothermic process or exothermic process. Now ionization on the other hand is always, if you take ionization, it is always endothermic process. Endo means inside, thermic means temperature. Electron in ionic solids, the sum of electrons and gain enthalpy and ionization enthalpy may be positive, but still crystal structures gets stabilized due to the energy released in the formation of crystal lattice. For example, ionization enthalpy for sodium plus G, formation from Nag is generally along with the sodium 495.8 kilojoule mole inverse of energy. Got my point? And while the electron gain enthalpy for the changes, if you take a chlorine G plus electron gain, okay, in case of chlorine, and it will be minus 348.7 kilojoule mole inverse only. The electron gain here, the process completely, sum of energy is completely changed. The sum of 2, which means for sodium it is 495.8, for chlorine it is minus 348.7. The sum of two energy changes are 147.1 kilojoule mole inverse is more than compensated for enthalpy. So for sodium chloride it will be minus 788 kilojoule mole inverse. Therefore energy released in the process is more than that. Okay, energy absorbed. So thus what we can say here, a qualitative measure of the stability. So the stability of an ionic compound is provided by the enthalpy of lattice formation. Okay, now in case the ionic bond formation or ionic compound formation, It is provided by enthalpy, we know that, but it is depending upon the octet of electrons around the ionic species in gaseous state only. Since lattice enthalpy plays a key role, enthalpy generally playing a key role in the formation of ionic compounds. Without this enthalpy, enthalpy is nothing but energy gain or energy loss. It is important whether it is exothermic enthalpy or endothermic enthalpy. It is important that we learn more about it. Finally, lattice enthalpy. What do you mean by that? Here in the previous slides we have seen lattice enthalpy. Lattice enthalpy of ionic solid. Let us take an ionic solid, any kind of solid, is defined by the energy required. So to completely separate 1 mole of if you want to separate 1 mole of a solid ionic compound into a gas, okay, here that energy is nothing but lattice enthalpy. For example, lattice enthalpy of sodium chloride is 788 kilojoule mole inverse. This means that 788 kilojoule of energy is required to separate 1 mole of solid or sodium chloride into 1 mole of sodium gram and 1 mole of chlorine gram into infinity distance. This process involves both the attractive forces between ionic opposite charges. There is an what we can call attractive forces occurring in between ions where opposite charges are there. So whereas if you take opposite charges plus or minus, repulsive forces are going to be occurring in between the charges. Whenever there are both attractive forces, suppose attractive forces between opposite charges, ions of opposite charges, and repulsive forces between ions like charge, generally it is very much common. So the solid crystal being 3-dimensional, okay, it is not possible to calculate lattice enthalpy directly from the interaction, okay, of forces attraction and repulsion only. Factors associated with the crystal geometry have to be included. Bond parameters, bond length. Bond length is defined as the equilibrium or distance between the nuclei of 2 bond atoms in molecule. Bond length are measured by spectroscopic. Bond length is generally measured by spectroscopic and X-ray diffraction, okay, and electron diffraction techniques. These techniques you will learn in the higher classes. Each atom of the bond, okay, whether it is a right angle or left angle or it is a 90 degrees angle, what is 45 degrees angle in between 2 atoms, each atom of the bonded pair contributes to the bond length. Finally, what I am telling you, in case of covalent bond, contribution from each atom is called covalent radius. What is that called? Covalent radius of that atom. The covalent radius is measured approximately a radius of an atom core which is in contact with the core of adjacent atom in bonded situation. The covalent radius is half of the distance between 2 similar atoms joined by covalent bond. Finally, what I am telling you, if you carefully see bond length in a covalent molecule A and B, see here, this is a A, atom A, and whereas this is atom B. Imagine this is atom A and this is atom B. Okay, this is the center. Okay, so let me rub this for your understanding once again. Okay, this is A, atom A, and this is atom B, and this is center. We would like to know the radius. Okay, for atom A, RA is the radius. For atom B, RB is the radius. Okay, distance between them from the center, that we have to know. Okay, you understood my point? Right. Here we have a formula for that. So R equal to, radius R equal to for atom A Ra plus for atom Rb. This formula applicable to a compound joined by covalent bond in a compound. Ra is referred, R is the bond length, Ra and Rb are the covalent radii of atoms in a covalent bond. A and B are respectively. Finally, what I am telling you, in the same molecule, van der Waals equation or van der Waals radius represents the overall size of the atom, which includes valence shell in non-bonded situation. Further, van der Waals radius is half of the distance. What is van der Waals radius? It is the half of the distance between two similar atoms in a separate molecule. Now, covalent and van der Waals radii of chlorine are depicted in the figure. I will show you that figure. Here you can see a covalent and van der Waals radii. You can see R equal to 99 pm. So this is a figure which depicts covalent and van der Waals radii. Okay. Some measurements are also given here. We have to take it. Finally, bond angle. What do you mean by that? The angle between the orbitals. The angle between the orbitals containing bonding electrons pairs around the central atom, generally called as the bond angle. Here, bond angle is expressed, if you take the bond angle, expressed in degree, which can be extremely determined by spectroscopic methods. Here, it is